Okay, so if you remember when we were talking about heat and work, we've looked at delta E and we've looked at the work calculation. Where we're going to put those together and do an equation for delta H, which is enthalpy. We've already talked about that delta H is a state function. It is symbolized as Q at constant pressure, and we assume that almost everything we do is at constant pressure. We can calculate enthalpy from a number of different ways: stoichiometry, calorimetry. We can look at tables of standard values, Hess's law, like the lab that we did yesterday, and bond energies. Basically what it's saying is that if you take your reactants that are reacting together, they're going to start giving off energy as they react, and they're going to gain energy until they get to something that's called the transition state, which is also called an activated complex. But they're going to reach this amount of energy, and that is called this amount, just like in the video that we watched, is the energy of activation, or better known as the activation energy. So that amount, this amount right here, which is from where the reactants, the amount of energy that the reactants started with to the amount of energy that the products now have, that is your delta H. So that's the amount of heat that is given off by the reaction, and that's the actual energy that we're really most interested in. So looking at exercise 4, exercise 4 says, okay, you add solid potassium hydroxide pellets to water, and you want to know what happens with this reaction. Well, we have energy over here on the product side. Well, if you have energy, if you have a number in kilojoules per mole, which is actually delta H, this is delta H, and because it's on the reactant side, that is telling you that that is being given off. So that means this is an exothermic reaction. And if it's exothermic, that means that we're going to have a negative delta H. So we're asking these questions now. Does the beaker get warmer or colder? Well, we just said it's exothermic, so it's going to get warmer. Is the reaction endothermic or exothermic? We've already said it's exo. Now, this is where it gets a little interesting. It says, what is the enthalpy change for the dissolution of 14 grams of potassium hydroxide? So if you put that in water and it dissociates, it breaks up, what amount of energy is being given off? Okay, so we start with what we're being given here, and we're given 14 grams. So this is a little bit of a stoichiometry reaction. So we're given 14 grams of potassium hydroxide. We need to change this to moles. So how many moles of KOH are there in the number of grams of KOH? So you've got to add this up, okay? What is the mass numbers? What are the mass numbers for all these? Well, hydrogen's 1, oxygen is 16, potassium is 39. Just straight from the periodic table. You add all those up, and you're going to get 56 grams. So this is 56 grams. We can cancel out our grams of KOH. 14 divided by 56, you put that in your calculator, you get 0.25 moles of KOH. So that's our molarity. So now we've got to take this and we've got to figure out, okay, well, how much actual energy, so what is this molar energy that's being released? Well, up here we know that it's 43 kilojoules per mole, okay, that is being given off, times our number of moles that we just calculated, 0.25 moles. So we cancel out our moles. So 43 times 0.25 and it is a negative 10.75 kilojoules. And we say that it's negative. This is one of those things that you just have to remember that if it is an exothermic, it's going to have a negative delta H. If it's an endothermic, it's going to be a positive delta H. So you have to assign a value, a negative or a positive, to your number based on these rules. So this is just something that you're going to have to remember. Not going away, and there's no way around it. You just have to remember those two things and be able to assign charges to your equations. All right, calorimetry. Coffee cup calorimetry is what we just did in lab, where you're calculating the amount of heat. So we're not going to spend a lot of time on that. You can read that. Basically, we worked this equation that Q equals MC delta T. So Q equals MCAT when you're looking at what's going on with this. So you've got to know the mass of the substance, you've got to know the change in temperature, and then C is going to be the specific heat of whatever solution you're using. For water, it's going to be 4.184. And the units for C are kind of weird, but it's joules over grams times degrees Celsius. Okay. All right, terms to know: heat capacity, that's just the energy required to raise the temperature by 1 degree Celsius. Specific heat capacity, that's the C that we were just talking about in MCAT. It's the quantity of heat transferred over the grams of material times the degree of temperature change. So that's where you get your joules per gram times degrees Celsius. Okay, energy or heat is Q. This is our equation, MCAT, MC delta T, where Q is the quantity of heat, M is your mass, delta T is your final minus your initial temperature, and C is your specific heat capacity of whatever solution. And like I said, for water, that's going to be 4.184. Water does have one of the highest specific heats known, and that is why we are able to have life on Earth, and also why, because of the fact that water has this really unique ability to hold in that heat, because it has such a high specific heat, it holds heat very, very well, which is why in the wintertime, why fish are able to survive under a big, thick layer of ice. And that's because of the fact that the water under the ice is still pretty warm, even though it's a fairly cold temperature. Units of energy, you do need to know what a calorie is. We typically, this is the number, the amount of heat needed to raise the temperature of 1 gram of water 1 degree Celsius. It is a very small unit. Usually we use a kilocalorie, especially when we're talking about food calories, and we symbolize that with a capital C. So do remember, though, that the amount of heat lost by any substance when it's put into water, it is gained by that water. So heat lost equals heat gained, our whole conservation of mass thing, you know, and of energy. Things cannot just be destroyed or lost. Here's another exercise. In a coffee cup calorimeter, 100 milliliters of 1 molar sodium hydroxide and 100 milliliters of 1 molar hydrochloric acid are mixed. Both solutions were originally at 24.6 degrees Celsius. So that's your initial temperature. So let's kind of write down what we know. Initial temperature is 24.6 degrees Celsius. After the reaction, the final temperature is 31.3 degrees Celsius. Assuming that all solutions have a density of 1 gram per centimeter cubed and a specific heat capacity of 4.184 joules per gram degree Celsius, calculate the enthalpy change. So we're looking at delta H. What is delta H? For the neutralization of hydrochloric acid by sodium hydroxide. And it tells you to assume that no heat is lost to the surroundings or the calorimeter. We know that actually doesn't happen, but for these equations, we usually just assume that all of the heat is conserved and it's all staying inside. So we're going to use our little formula, Q equals MC delta T. So Q equals MCAT. Mass, all right, well, here's where we got to think about this. Well, your mass, you have 100 milliliters of water, or of sodium hydroxide, and 100 milliliters of hydrochloric acid. So that's 200 milliliters when we add those together. So when you put the 100 milliliters of sodium hydroxide and the 100 milliliters of hydrochloric acid together, that makes 200 milliliters. Well, it told us to assume that the density is 1. Well, if the density is 1, then 200 times 1 is 200. So that's 200 grams. So that's our mass of our solution. So we have 200 grams of a solution times our C.
I have one more announcement before clubs meet. Any ag students who sold ham and turkeys need to make plans to come by and pick theirs up before 6:30 p.m. this evening in the ag shop.
We multiply that by C for water, which is the specific heat capacity of 4.184 joules per gram degree Celsius. And then we multiply that by delta T. So 31.3 minus 24.6. If you put that in your calculator, you get 6.7 degrees Celsius. Our degrees Celsius cancels, our grams cancel, we're left with joules. So Q equals, when you multiply all that together, that equals 5,606 joules. Let's go ahead and change that to kilojoules. So 5.6 kilojoules. And this is an exothermic reaction because our final temperature is higher than our initial. So that needs to be a negative. And that is our delta H. Q is delta H. So there's our answer, negative 5.6 kilojoules. Exercise 6. You've got 1 mole of methane, CH4, is burned at constant pressure, so we don't have to worry about the pressure. 890 kilojoules per mole of energy is released as heat. And so it says calculate delta H for a process in which 5.8 grams of methane is burned at constant pressure. So we're going to start with, this is kind of a stoichiometry problem. We're starting with 5.8 grams. That's what we know. And this is CH4. And we need to calculate the mass of CH4. Well, carbon is 12. Hydrogen is 1, but we've got 4 of them, so that's 4, so that's 16. So that's 16 grams of CH4 in 1 mole of CH4. And then we're looking at the other thing that we know, which is 890 kilojoules per mole. So if we have moles there, so we can cancel our grams. So we have moles there, we need to put moles down here. And then we're going to go to 890 kilojoules per mole. So now our moles cancel. So we're left with 5.8 times 890. 8 times 890 divided by 16. That is 320 kilojoules per mole of your reaction. And it is a negative because it's talking about giving off heat. So it's an exothermic reaction. exercise 7. All right, when 1 liter of 1 molar BaNO3 solution at 25 degrees Celsius is mixed with 1 liter of 1 molar Na2SO4 solution at 25 degrees Celsius in a calorimeter, the white solid BaSO4 forms and the temperature of the mixture increases. All right, that means this is going to be an exothermic reaction, so we know it's going to have a negative delta H right off the bat because it's talking about it increasing. So we're saying, assuming that the calorimeter absorbs only a negligible amount of heat and that the specific heat capacity of the solution is 4.184 or 4.18, and that the density of the final solution is 1 grams per milliliter, calculate the enthalpy change per mole of BaSO4 formed. Okay, so we know we've got to calculate this. We've got to use our Q equals MCAT. So we need to know what is our mass of our solution. Well, we have 1 liter here combining with 1 liter. Well, a liter is 1,000 milliliters. So we've got to have this in milliliters. So we've got 1,000 milliliters of this, 1,000 milliliters of this. 1,000 plus 1,000 is 2,000. It's 1 gram per milliliter. So that just means we've got 2,000 grams of the solution. We're multiplying it by 4.184. And then we're going to multiply it by delta T. Well, our temperature went from 25 to 28.1. That's just a 3.1 degree difference. So if we multiply that out, you get 25,940 joules, which is going to be, that rounds to about 26 kilojoules. And we already know that it's negative, so our delta H has to be negative, so it's a negative 26. Okay? We're going to stop there.